students. First of all, I welcome you all to my second video on the chapter Biomolecules. As you know, in the first video, we discussed classification of carbohydrates, glucose, preparation and properties of glucose. Based on the chemical properties of glucose, we derived the structure of glucose. That is, I introduced the open chain structure of glucose in the previous video. That will be written like this. Look here, this is open chain structure of, yes it is the glucose there with the 6 carbon atoms or the with exact spatial arrangement of OH groups at asymmetric carbon atoms, right? Look at this. This is the open chain structure of, yes it is glucose here. Or the this is H. This will be OH. This will be H and it will be H. This is open chain structure of glucose. This is carbon atom number 1. This is 2. This is 3, 4, 5 and 6. As far as glucose is concerned, it contains 4 asymmetric carbon atoms. That is, asymmetric carbon atoms are those carbon atoms which will be attached with 4 different groups, is it not? A molecule of glucose contains 4 asymmetric carbon atoms. Just observe the spatial arrangement of OH groups at the asymmetric carbon atoms. This is the open chain structure of glucose. This open chain structure of glucose has got a certain configuration. That is, the spatial arrangement of atoms or groups at the asymmetric carbon atoms of a given molecule is called configuration. In order to assign configuration to the glucose, we have many methods, but as per your NCERT textbook, we are supposed to make use of one method of assigning configuration to the stereoisomers or optical isomers. It will be D and yes it is L notations. This is one of the methods that I can make use of in order to assign configuration to the glucose here. As far as this DL method of assigning configuration is concerned, in this particular method, we make use of simplest possible, yes it is carbohydrate with the 3 carbon atoms and 1 asymmetric carbon, that is glyceraldehyde. I can make use of this configuration of glyceraldehyde in order to assign configuration to the, yes it is monosaccharides, or you can say that optical isomers. Here this glyceraldehyde has got 1 asymmetric carbon atom. Just observe, in this particular structure, OH group is on the right side of the asymmetric carbon atom, right? And this is what we call it as plus glyceraldehyde. This is what we call it as plus glyceraldehyde. Okay, now? Its enantiomer is got, yes it is, its enantiomer is, enantiomer of this particular glyceraldehyde is this. Yes, this is the mirror image of this particular, yes it is isomer. In this particular structure, just observe glyceraldehyde. In this particular configuration, just observe the OH group is on the left side, is it not? Left side of the asymmetric carbon atom. This is what we call it as minus glyceraldehyde. This is minus glyceraldehyde. This plus sign indicates that is optical rotation of this glyceraldehyde. That is, this glyceraldehyde is dextrorotatory. Its mirror image is levorotatory. Just observe, yes it is the configuration of the asymmetric carbon atom. Here OH group is on the right side, here OH group is on the left side. I can make use of this configuration of glyceraldehyde in order to assign, yes it is configuration to the, yes it is monosaccharides. And of course, as far as the D isomers are concerned, D isomers are the chemical substances. D isomers are chemical substances which will be chemically correlated to the, yes it is plus glyceraldehyde. Similarly, L isomers are those chemical compounds. L isomers are those chemical compounds which will be chemically correlated to the, yes it is minus glyceraldehyde. In order to assign configuration to the glucose, by D and L method, D and L notations method. I need to compare configuration of lowest asymmetric carbon atom, configuration of, yes it is lowest asymmetric carbon atom with that of the, yes it is glyceraldehyde. Just observe, as far as glucose is concerned, this is lowest asymmetric carbon atom, or you can say highest numbered asymmetric carbon atom. 1, 2, 3, 4, 5. This is highest numbered asymmetric carbon atom, or lowest asymmetric carbon atom. The configuration at the lowest asymmetric carbon atom matches with, yes it is plus glyceraldehyde. The configuration at the lowest asymmetric carbon atom matches with, yes it is plus glyceraldehyde. Just observe, in plus glyceraldehyde, OH group is on the right side of the asymmetric carbon atom. Here in glucose also, at lowest asymmetric carbon atom, OH group is on the right side. Therefore, it is, yes it is D-glucose we call it as D-glucose. Similarly, if the configuration at lowest asymmetric carbon atom matches with minus glyceraldehyde, then we are going to assign L notation for that particular, yes it is isomer, for that particular stereoisomer. So this is what we call it as the method, that is D and L notation method, in order to assign configuration to the, yes it is monosaccharides. And of course glucose has got, yes it is D-glucose it is. As far as D is concerned, D and L notations, they are nothing to do with, yes it is optical rotation. D and L notations, they are nothing to do with optical rotation. They simply indicate configuration at lowest asymmetric carbon atom. They simply indicate configuration at lowest asymmetric carbon atom. So don't think that, D stands for dextrorotatory, L stands for levorotatory, not like that. They do not indicate anything about the optical rotation. They simply indicate, yes it is configuration only. For example, in the case of, yes it is fructose, say for example, let me show you one example. Look at this. This is fructose. Look at this. This is fructose. Lowest asymmetric carbon atom is this. Look at the configuration. At the lowest asymmetric carbon atom of fructose, your OH group is on the right side. This configuration matches with plus glyceraldehyde. Therefore, it is also, yes it is D-fructose. It is also D-fructose. But actually, fructose is levorotatory. Fructose is levorotatory. In order to indicate optical rotation of this fructose, we make use of one more sign, that is D minus fructose. Like that we use. We make use of one more sign, that is D minus. D stands for configuration. OH group at the lowest asymmetric carbon atom is on the right side. Minus indicates that fructose is levorotatory. Look here, as far as glucose is concerned, glucose is, yes it is D plus glucose it is. And of course, glucose is D plus glucose. D stands for OH group at the lowest asymmetric carbon atom on the right side, and plus indicates what we call it as dextrorotatory. Glucose is dextrorotatory. That's why we write plus here. Minus indicates what? Levorotatory nature of, yes it is fructose. Fructose is levorotatory. Therefore, we use minus sign here. Like that, D and L notations, they are nothing to do with optical rotation of an optical isomer. They simply indicate configuration at the lowest asymmetric carbon atom. Configuration at the lowest asymmetric carbon atom. So this is what we call it as one method in order to assign configuration to the, yes it is monosaccharides, or you can say that optical isomers. And that is what we call it as, yes it is D and L notations. Now at this moment, we'll go to the next discussion, that is cyclic ring structure of glucose there. Yes. Now let us see, next discussion under glucose is cyclic ring structure of glucose. In the previous discussion, we derived the open chain structure of glucose. This is open chain structure of glucose. Just observe, open chain structure of glucose contains aldehyde group, primary alcoholic group, or the 4 secondary alcoholic groups, or the totally 5 alcoholic groups we have. All these discussions we had in the previous video. As far as open chain structure of glucose is concerned, it explains almost all the properties of glucose, but still, this open chain structure of glucose does not explain some of the reactions of glucose and some of the facts of glucose. Let us see some facts or reactions which cannot be explained on the basis of open chain structure of glucose. One reaction is, as far as glucose is concerned, even though it contains aldehyde group, glucose does not answer Schiff's reagent test. That is, glucose does not answer Schiff's reagent test. This is one of the reactions that we cannot explain on the basis of, yes, it is open chain structure. Just observe, open chain structure of glucose contains aldehyde group. Even though aldehyde group is present, a glucose does not answer Schiff's reagent test. As far as the Schiff's reagent test is concerned, Schiff's reagent test is used to confirm, yes, it is aldehydes. All aldehydes answers Schiff's reagent test. That means aldehydes turn Schiff's reagent pink. When aldehyde is added to the Schiff's reagent, the solution of Schiff's reagent becomes red in color or pink in color. But glucose does not answer, yes, it is Schiff's reagent test. It does not turn Schiff's reagent pink. That is one chemical reaction that we cannot explain on the basis of, yes, it is open chain structure. And second reaction that we cannot explain on the basis of open chain structure is, even though aldehyde group is present in glucose, glucose does not form white crystalline precipitate with saturated solution of sodium bisulfite. But aldehydes form white crystalline precipitate with saturated solution of sodium bisulfite. That is, glucose does not form white crystalline precipitate. Yes, it is with saturated solution of sodium bisulfite, NaHSO3. The organic compounds containing aldehyde groups will form white crystalline PPT with saturated solution of sodium bisulfite. But glucose, even though it contains aldehyde group, it does not form white crystalline PPT with saturated solution of sodium bisulfite. That's why this property of glucose cannot be explained by, yes, it is open chain structure. And the fourth observation is, that is glucose pentacetate does not react with hydroxylamine. In the case of glucose pentacetate contains aldehyde group. Even though aldehyde group is present in glucose pentacetate, it does not react with hydroxylamine. Aldehydes and ketones will react with hydroxylamine. This property of glucose cannot be explained by open chain structure. And the fourth observation is, the fourth fact that we cannot explain on the basis of open chain structure of glucose is, glucose exists in the form of, yes, it is alpha and beta forms. Yes, it is, we have alpha glucose and beta glucose with different physical and chemical properties. For example, alpha glucose or alpha D glucose has a melting point of, yes, it is 419 kelvins, whereas beta D glucose will have a melting point of, yes, it is 423 kelvins. The existence of alpha D glucose and beta D glucose cannot be explained on the basis of open chain structure. Therefore, in order to account for these reactions, in order to account for these properties of glucose and these facts of glucose, a scientist Fisher has given one structure, that is cyclic ring structure, to the glucose. And as far as these chemical reactions are concerned, these reactions indicate absence of aldehyde group in, yes, it is glucose. Howda? ಅಕಸ್ಮಾತ್ ಏನಾದರೂ ಗ್ಲೂಕೋಸ್ ಅಲ್ಲಿ aldehyde group ಇದ್ದಿದ್ರೆ ಏನಾಗಬೇಕಿತ್ತು? Glucose must form pink color with Schiff's reagent. Glucose must form crystalline PPT with saturated solution of sodium bisulfite. Glucose pentacetate must react with hydroxylamine. ಹೌದಾ? ಆದ್ರೆ so these observations indicate the absence of aldehyde grouping. Yes, it is glucose there. Because of that, there is a need of one more structure to the glucose which can explain these properties of glucose. Because of that, the scientist Fisher give, yes, it is cyclic ring structures to the glucose. Let us see cyclic ring structures of glucose. Based on these cyclic ring structures, we can account for the, yes, it is drawbacks of, yes, it is open chain structure of glucose. Before going to that particular discussion, let me see the differences between, yes, it is alpha D glucose and beta D glucose. What I said, the melting point of, yes, it is alpha D glucose is, yes, it is 419 kelvins. Melting point of, yes, it is beta D glucose is, yes, it is 423 kelvins. Okay, now this is the difference in properties of alpha D glucose and beta D glucose. Apart from that, alpha D glucose can be prepared by crystallization of concentrated glucose solution at 303 kelvins. When concentrated solution of glucose is crystallized at 303 kelvins, then you are going to get alpha D glucose. Similarly, beta D glucose can be obtained by the crystallization of, yes, it is hot and saturated solution of glucose at, yes, it is 371 kelvins. That is, when hot and saturated solution of glucose is crystallized at 371 kelvins, then you are going to get beta D glucose. This is how alpha D glucose and beta D glucose can be prepared. Okay, now with this information, we'll go to the, yes, it is cyclic ring structures of glucose. Yes, with that information, we'll go to the cyclic ring structures of glucose there. Okay, now let me write the cyclic ring structures to the glucose. This is open chain structure of glucose. I can make use of this open chain structure in order to write cyclic ring structure to the glucose, right? In order to write, yes, it is cyclic ring structure to the glucose, the alcoholic group at the fifth carbon atom will be added to the, yes, it is carbonyl group here. This is aldehyde group that contains C double bond O. Oxygen is more electronegative than, yes, it is carbon. Therefore, oxygen gets negative charge, carbon gets positive charge. Just observe, this is alcoholic group, right? And just observe, this is alcoholic group. OH group is polar, right? Oxygen is more electronegative than hydrogen. Therefore, hydrogen can be eliminated in the form of H plus. Oxygen gets negative charge. Oxygen mele minus ಇದೆ. Hydrogen is removed in the form of H plus. Just observe, O minus of carbonyl group attracts H plus. O minus of carbonyl group attracts H plus. Therefore, C double bond O is converted to COH ಆಗುತ್ತೆ. And this O minus, that is negative charge on the, yes, it is this oxygen atom with negative charge. This oxygen atom at the fifth carbon atom is attracted by positive charge of the carbon. This positively charged carbon of carbonyl group is attracting, yes, it is O minus. Thereby, addition of alcoholic group across the carbonyl group takes place. That results in the formation of addition compound called hemiacetal. That leads to the formation of hemiacetal. When alcohols are added to the carbonyl compounds, you are going to get hemiacetals. Like that, here you are going to get hemiacetal ring of, yes, it is glucose here. When alcoholic group at the fifth carbon atom is added across the carbonyl group. And just let me show that, yes, it is. Let me show that, right? Look here. Just you write plus, first you write carbon chain, yes. This is CH2OH. And this positively charged carbon is attracting, yes, it is negatively charged oxygen. Thereby, there is a formation of, yes, it is bond between, yes, it is negatively charged oxygen and of course positively charged carbon. Like this, that is cyclization takes place. Like this, cyclization takes place. This is how hemiacetal ring formation takes place. The negatively charged oxygen atom at fifth carbon atom is attracted by positively charged carbon of carbonyl group. Thereby, cyclization takes place. And this O minus, this H plus is attracted by O minus, and thereby O minus is converted to, yes, it is OH group there. The O minus is the H plus attract ಮಾಡ್ಕೊಂಡ್ಬಿಟ್ಟು OH ಆಗುತ್ತೆ. Yes, and double bond is converted to single bond, and this O minus is attracted by, yes, it is positively charged carbon like this, and that results in, yes, it is cyclic ring with 6 atoms in a cyclic ring. Look at this This cyclic ring contains 5 carbon atoms and 1 oxygen. And this is 6-member cyclic ring. And of course, you write remaining groups as it is. This is H. This is carbon number 1. This is number 2. This is number 3. This is 4 and this is 5. And 5th carbon atom, oxygen, O minus is attracted by, yes it is C plus. Thereby O minus is attracted by C plus. There is a hemiacetal ring formation. Here this 5th carbon atom is characterized by hydrogen. You write it as 4th carbon atom alli nimage OH ide. 3rd carbon atom alli H ide. 2nd carbon atom alli OH ide. Remaining things we write as it is. And if it is OH here, it will be H here. It is H here, therefore it will be OH. OH irodrinda illi H baritini. This is what we call it as cyclic ring structure of, yes it is Fisher cyclic ring structure of glucose here. And due to the cyclization, just observe, one new asymmetric carbon atom is formed here. This is new asymmetric carbon atom. This asymmetric carbon atom is anomeric carbon atom. This asymmetric carbon atom is anomeric carbon atom. Anomeric carbon atom is asymmetric carbon atom in cyclic ring. It was carbonyl carbon in open chain structure. Just observe, because due to the formation of, yes it is new asymmetric carbon atom, there are 2 possible configurations that, yes it is asymmetric carbon atom in cyclic ring structure. Here in this case, OH group is on the right side. OH group is on the right side of the anomeric carbon atom, and therefore it is called, yes it is alpha D glucose. It is called as alpha D glucose. Alpha D glucose is what we call it as cyclic ring structure, in which OH group at the anomeric carbon atom is on the right side. Similarly, I can write one more possible structure, one more possible cyclic ring structure. Yes, I can write one more possible cyclic ring structure to this. Yes, that is by just keeping OH group at the, yes it is anomeric carbon atom on the, yes it is left side. This is CH2OH. This is OH. And of course cyclization takes place at the 5th carbon atom. This is what we call it as cyclic ring structure. And here it is H. This is OH. This is H. This is OH. Here OH on the right side at the anomeric carbon atom. Just you keep your OH on the left side of the anomeric carbon atom. This is asymmetric carbon atom. This is anomeric carbon atom. And it will be H here. And remaining as it is. This is H. This is OH. It will be H. Here in this particular cyclic ring structure, OH group at the anomeric carbon atom will be on the left side. Therefore it is beta D glucose. Therefore it is beta D glucose, right? Like that, 2 possible cyclic ring structures assigned to glucose here. 2 possible cyclic ring structures assigned to glucose by Fisher. I can make use of these 2 cyclic ring structures in order to explain, yes it is, the drawbacks of the open chain structure. Just observe, in the cyclic ring structure, you don't find any aldehyde group. Open chain structure aldehyde group is there, but cyclic ring structurally no aldehyde groups are present. Therefore, glucose does not answer a strip reagent test. Glucose does not form white crystalline PPD with sodium bisulfite. Glucose pentacetate does not react with, yes it is the hydroxylamine, due to the absence of aldehyde group in, yes it is cyclic ring structures. At the same time, I can make use of these that is cyclic ring structures in order to account for the existence of, yes it is alpha and beta D glucoses. Just observe, if OH group at the anomeric carbon atom is on the right side, it will be alpha D glucose. If OH group at the anomeric carbon atom on the left side, it will be beta D glucose. This is what we call it as cyclic ring structures of glucose there. And this structure was proposed by Fisher itself. Yes. Now at this moment, I can make use of this particular Fisher cyclic ring structures in order to write Howard structures of glucoses, right? In order to write Howard structures to the glucose. We'll see one by one, right? Let me write Howard ring structure to the alpha D glucose. In order to write Howard ring structure to the alpha D glucose, I can make use of cyclic ring structure of, yes it is alpha D glucose. Just observe, in the cyclic ring structure, we have 5 carbon atoms and 1 oxygen atom. Totally, it is a 6-membered ring it is. And the possible stable 6-member cyclic ring will be, yes it is cyclic hexagon. it will be cyclic hexagon with one oxygen atom in the cyclic ring. Look at this. This is what we call it as the cyclic hexagon for the stable cyclic hexagon for the 6-membered acetyl cyclic compound. ಹೌದಾ, ಇದು 6-membered cyclic ring ಆಗಿರೋದ್ರಿಂದ 6-membered cyclic compound ಆಗಿರೋದ್ರಿಂದ I can make use of this stable 6-membered cyclic ring as cyclic hexagon. ಹೌದಾ, this is carbon atom 1, this is carbon atom 2, this is carbon atom 3, this is carbon atom 4, and this is carbon atom 5. Just observe, in the cyclic ring structure, oxygen is attached to first and fifth carbon atoms. ಹೌದಾ, here also oxygen is attached to first and fifth carbon atoms. ಹೌದಾನೆ, ಹೌದಲ್ವಾ? Right? Just observe, some groups are on the right side of the cyclic ring structure, some groups are on the left side of the cyclic ring structure. In order to write, yes, it is in Haworth cyclic ring structure, these groups attached to the asymmetric carbon atoms will be written above and below the plane of the cyclic ring. These groups attached to the asymmetric carbon atoms will be written above and below the plane of the cyclic ring. Now, just observe, in the case of first carbon atom, here, this is first carbon atom, OH is on the right side. Those groups which are on the right side of the cyclic ring structure will be written below the plane of the acetyl cyclic hexagon in Haworth structure. Cyclic ring structure ಅನ್ನ Haworth ring structure ಆಗಿ ಕನ್ವರ್ಟ್ ಮಾಡಬೇಕಾದ್ರೆ ಯಾವ ಗ್ರೂಪ್ಸ್ ರೈಟ್ ಸೈಡ್ ಅಲ್ಲಿ ಇದಾವೋ ಅವುಗಳನ್ನೆಲ್ಲವೂ ಕೂಡ ಬಿಲೋ ದ ಪ್ಲೇನ್ ಬರೀಬೇಕು. ಜಸ್ಟ್ ಅಬ್ಸರ್ವ್, OH group is on the right side, therefore in the first carbon atom OH is below the plane. Second carbon atom OH is below the plane. Third carbon atom H below the plane. Fourth carbon atom OH below the plane. ಹೌದಾ? And of course, as far as CS2H group is concerned, CS2H group is written always above the plane if cyclization takes place from right side. If cyclization takes place from right side, CS2H group should be written always above the plane there. This is, and of course, this is carbon atom number 5 and it will be carbon atom number 6. Okay? This is the 6th carbon atom. Okay? And the remaining groups, here, these groups, they are on the left side of the cyclic ring, should be written above the plane. Here it is OH, therefore it should be H. It should be H. Here H there, therefore it should be OH. Here OH there, therefore it should be H. Here CS2OH there, remaining is hydrogen, that should be written below the plane. This is what we call it as the alpha D glucose structure. How about the structure of alpha D glucose? Just observe, this particular cyclic ring matches with one heterocyclic acetate compound, that is pyron. This is structure of pyron. This is structure of pyron. Just observe, pyron contains 6 carbon atoms and 1 oxygen atom in its cyclic ring. Therefore, this particular structure matches with pyron. This is heterocyclic compound known as pyron. Therefore, this particular structure is known as, yes, it is alpha D glucopyranose. This is alpha D glucopyranose. Of course, because this structure is almost similar to the, yes, it is a structure of, yes, it is heterocyclic compound known as pyron. That's why it is pyranose ring structure of alpha D glucose. This is alpha D glucopyranose. Okay? And if you want to write the beta D glucopyranose, just observe, this is anomeric carbon atom. In the case of alpha D glucopyranose, OH group is below the plane. Okay? And as far as beta D glucopyranose is concerned, beta D glucopyranose simply you write OH group above the plane, hydrogen below the plane, and this is what we call it as beta D glucopyranose. The main difference between alpha D glucose and beta D glucose is, that is configuration at the anomeric carbon atom. In the case of alpha D glucose, OH group at the anomeric carbon atom is below the plane. In the case of beta D glucopyranose, OH group at the anomeric carbon atom is above the plane. This is the major difference between alpha D glucopyranose and beta D glucopyranose. Just observe. ಇದೆಲ್ಲವೂ ಕೂಡ ಎಕ್ಸಾಮ್ ಅಲ್ಲಿ ಕೇಳ್ತಾರೆ. ರೈಟ್ ದಿ ಹಾವರ್ತ್ ರಿಂಗ್ ಸ್ಟ್ರಕ್ಚರ್ ಆಫ್, ಎಸ್ ಇಟ್ ಈಸ್ ಆಲ್ಫಾ ಡಿ ಗ್ಲೂಕೋಸ್ ಅಂಡ್ ಬೀಟಾ ಡಿ ಗ್ಲೂಕೋಸ್ ಅಂತ ಕೇಳ್ತಾರೆ. ಆಗ ಈ ಸ್ಟ್ರಕ್ಚರ್ಸ್ ಅನ್ನ ಬರೀಬೇಕು. ನೋ ಡೌಟ್ we written these structures based on, yes, it is cyclic ring structure, but ನೀವು ಎಕ್ಸಾಮ್ ಅಲ್ಲಿ ಜಸ್ಟ್ ಹಾವರ್ತ್ ರಿಂಗ್ ಸ್ಟ್ರಕ್ಚರ್ ಬರೆದ್ರೆ ಸಾಕು. ನಾನು ಕೆಲವು ಐಡಿಯಾಸ್ ಹೇಳ್ಕೊಡ್ತೀನಿ ನಿಮಗೆ, ಹೌ ಟು ರೈಟ್, ಎಸ್ ಇಟ್ ಈಸ್ ಆಲ್ಫಾ ಡಿ ಗ್ಲೂಕೋಸ್ ಸ್ಟ್ರಕ್ಚರ್ ಅಂಡ್ ಬೀಟಾ ಡಿ ಗ್ಲೂಕೋಸ್ ಸ್ಟ್ರಕ್ಚರ್ಸ್. ಓಕೆನಾ? ಡೈರೆಕ್ಟ್ಲಿ, that is in order to write alpha D glucopyranose, first you write cyclic hexagon ಈ ರೀತಿ cyclic hexagon ಬರೆದ್ಬಿಡಿ ಹೌದಾ ಈ ರೀತಿ cyclic hexagon ಬರೆದ್ಬಿಟ್ಟು write the points above the plane and below the plane. This is carbon atom number 1, this is 2, this is 3, this is 4, this is 5, and of course CH2H is always above the plane. ಇದು ಫಸ್ಟ್ ಬರ್ಕೊಂಡ್ಬಿಡಬೇಕು ಓಕೆನಾ. ಈಗ ನೋಡಿ ನಾನು ಆಲ್ಫಾ ಡಿ ಗ್ಲೂಕೋ ಪೈರನೋಸ್ ಬರಿತಾ ಇದ್ದೀನಿ. ಆಲ್ಫಾ ಡಿ ಗ್ಲೂಕೋಸ್ ಅಥವಾ ಆಲ್ಫಾ ಡಿ ಗ್ಲೂಕೋ ಪೈರನೋಸ್ ಬರಿತಾ ಇದ್ದೀನಿ. ಜಸ್ಟ್ ಅಬ್ಸರ್ವ್, ದಿಸ್ ಇಸ್ ಕಾರ್ಬನ್ ಆಟಮ್ ನಂಬರ್ 1, this is another carbon atom, this is fourth carbon atom, and just you add OH groups, 2 OH groups, they are at the cis positions. 1,4 positions ಅಲ್ಲಿ OH groups are at the cis positions ಅಲ್ಲಿ ಇದೆ, they are on the same side. 2-3 position ಅಲ್ಲಿ OH groups are at the trans positions. ನೋಡಿ at 1-4 positions OH groups are cis to each other. ಹೌದಾ at 2-3 positions ಅಲ್ಲಿ OH groups are trans to each other. ಹೌದಾ ಇಲ್ಲಿ ನೋಡಿ ಎರಡು OH groups 1-4 position ಅಲ್ಲಿ ಒಂದೇ ಸೈಡ್ ಇದೆ, 2-3 positions ಅಲ್ಲಿ ಆಪೋಸಿಟ್ ಇದೆ. ಇಷ್ಟು ಬಂದ್ರೆ ಸಾಕು, ರಿಮೈನಿಂಗ್ ಬರಬಹುದಲ್ಲ. ಇಲ್ಲಿ OH ಇದ್ರೆ ದಿಸ್ ಇಸ್ H, ಇಲ್ಲಿ OH ಇದೆ ಇಟ್ ಇಸ್ H, ಇಲ್ಲಿ OH ಇದೆ ಇಲ್ಲಿ H ಬರಬೇಕು, ಇಲ್ಲಿ OH ಇದೆ ಇಲ್ಲಿ H. This is what we call it as, and of course don't forget to write, yes it is H here. This is alpha D glucopyranose. Beta ಬರಿಬೇಕಾ, just change ಮಾಡಿ position, ಇದು H ಬರೀರಿ ಇಲ್ಲಿ OH ಬರೀರಿ. This is what we call it as beta D glucopyranose. Like that you can write how are three structure to the, yes it is glucose there. Yes ಅರ್ಥ ಆಯ್ತು ಅನ್ಕೋತೀನಿ ಹೌದಾ. So this is what we call it as how are three structure of glucose there. Yes, now at this moment we'll go to the one more monosaccharide, that is fructose. One of the monosaccharides, and of course and fructose is a sweetest natural occurring, yes it is sugar. This is fructose howda, and it is also known as levulose because fructose is levorotatory. It rotates plane of the plane polarizer right in anti-clockwise direction, therefore it is levulose because of levorotatory nature of, yes it is fructose there. As far as fructose is concerned, first you write open chain structures. Yes, this fructose is characterized by, yes it is 2 primary alcoholic groups. Fructose is characterized by 2 primary alcoholic groups at the terminal carbon atoms. Carbonyl group is at the second position. This is second position, that is carbonyl group is at the second position, right? Here it is, yes, remaining OH and OH, similar to that in the case of glucose. Next it will be H, here it is OH, this is H and it will be H. Glucose ಅಲ್ಲಿ ಹೇಗೆ OH hat trick dot ball one more wicket ಅಂತ ಹೇಳ್ತಿದ್ದಲ್ಲ, ಅದೇ ತರ ಇಲ್ಲೂ ಕೂಡ ಮೇಂಟೈನ್ ಮಾಡಬಹುದು. OH H ಇಲ್ಲಿ C double bond ಬಂದ್ಬಿಡುತ್ತೆ. Yes ಹೌದಾ, just observe in the case of glucose aldehyde group was at the first position, but here in the case of fructose keto group is at the, yes it is second position. ಅದನ್ನ ಗಮನಿಸಿ. This is what we call it as D minus fructose. It is, this is D minus fructose. D ಯಾಕೆ ಬರೆದೆ, OH group at the lowest asymmetric carbon atom is at the right side, therefore it is D isomer. Minus because it is levorotatory out ತಾನೆ. And just write the cyclic ring structure to the, as it is this fructose here. And ಗೊತ್ತಿದೆ as it is, during cyclization, look at this, oxygen gets negative charge, carbon gets, yes it is positive charge. Cyclization can be done by adding OH group across the carbonyl group howda. And of course this is first carbon, second, third, fourth and fifth carbon atom out ತಾನೆ. Look at this, the OH group of the fifth carbon atom, right? And this will be removed in the form of H plus, which H plus will be attracted by CO minus. Look at this, this is yes it is CH2OH howda. Look at this is carbon atom number 5. Here we have, yes it is oxygen howda. H plus is removed, hydrogen is removed in the form of H plus, it will be attracted by CO minus. Again agate, CO minus becomes COH. This is second carbon atom howda. CO minus becomes COH. To this second carbon atom we have CH2OH group here. This is CH2OH group. This is carbon atom number 1 out tane. Positive part of positively charged carbon is attracting negatively charged oxygen, thereby cyclization takes place. Thereby cyclization takes place between fifth and second carbon atom of, yes, it is fructose. Just observe, in the cyclic ring we have 5 atoms, 4 carbon atoms and 1 oxygen. This is 5-member cyclic ring. And you write remaining things as it is. This is H, this will be OH, this will be H. Nodi, ಇಲ್ಲಿ cyclization ಆಗಿದೆ. O- is attracted by C+. ಹೌದಾ? O- is attracted by C+. Fifth carbon atom ಅಲ್ಲಿ, fourth carbon atom ಅಲ್ಲಿ ಏನಿದೆ? OH group is on the right side, OH on the right side here. Third ಅಲ್ಲಿ hydrogen on the right side, third ಅಲ್ಲಿ hydrogen on the right side. Here it is right side. ಹೌದಾ? If it is hydrogen, it will be OH. This will be H. This is what we call it as cyclic ring structure of, yes, it is fructose here. Here, this is anomeric carbon atom. As I said, anomeric carbon atom is asymmetric carbon atom in cyclic ring structure, which was carbonyl carbon in open chain structure. How's asymmetric carbon atom in cyclic ring structure, which was carbonyl carbon in open chain structure, and this is what we call it as anomeric carbon atom. How's and this is alpha D fructose. It is. This is alpha D fructose because OH group at the anomeric carbon atom is on the right side. And one more possible structure, and for that particular cyclic ring, you know, that is one more possible cyclic ring structure will be, yes, it is. Look at this. This is yes, it is CS2OH. Howda? Here it is a cyclization. Howda? Cyclization takes place between second carbon atom and fifth carbon atom, right? This is, yes, it is OH now, and it will be CS2. Yes, it is OH. The cyclization takes place like this. Illi nodi, OH group right side ide, illi OH group left side ide. Howda? Illi CS2OH left side ide, illi CS2OH right side ide. Howda? This is H. This will be OH. Remaining as it is, Barari. This is OH. It will be H. Here, this is what we call it as beta D fructose. This is what we call it as beta D fructose. Here, OH group at the anomeric carbon atom is on the left side. Therefore, it is beta D fructose. This is carbon atom number 2. This is 1. This is 3. This is 4. This is 5. And this is 6. So these two are, you know, cyclic ring structures of, yes, it is fructose here. And you can convert this cyclic ring structure into, yes, it is Haworth ring structure. Let me write Haworth ring structure to the, yes, it is fructose now, right? Let me write Haworth ring structure to the, yes, it is fructose. As you know that in the case of fructose, there are 5 atoms in a cyclic ring, and stable 5-member cyclic ring will be, yes, it is cyclic pentagon. Yes, cyclic pentagon is a stable cyclic ring for the, yes, it is 5-membered cyclic rings. For 5-member cyclic rings, you know, the stable structure will be, yes, it is cyclic pentagon. Look at this. This is 1 carbon, 2 carbon, 3, 4 carbon atoms and 1 oxygen. And the groups attached to the, yes, it is carbon atoms will be written above and below the plane. The groups attached to the carbon atom will be written above and below the plane. Look at this. This is second carbon atom. Oxygen is attached to second and fifth carbon atom. Therefore, it is second carbon atom. It should be fifth carbon atom because oxygen should be attached to second and fifth carbon atom. And here in this case, OH group is on the right side. Therefore, it should be written below the plane. And therefore, CS2H should be above the plane. And this CS2H group should be always written above the plane if cyclization takes place from right side. If cyclization takes place from right side, CS2H group should be written always above the plane. And this is carbon atom 6. This is carbon atom 6. Here in the third carbon atom, look at this. This is third carbon atom. H is there on the right side. Therefore, H here. In the fourth carbon atom, OH is there. Therefore, it is OH. In the fifth carbon atom, CS2H is above the plane. Hydrogen should be below the plane. Remaining, ಇಲ್ಲಿ H ಇದೆ, ಅದಕ್ಕೋಸ್ಕರ ಇಲ್ಲಿ OH ಇರುತ್ತೆ. ಇಲ್ಲಿ OH ಇದೆ, ಅದಕ್ಕೋಸ್ಕರ ಇಲ್ಲಿ H ಇರ್ತದೆ. So this is what we call it as alpha D fructofuranose. It is. It is not pyranose. It is furanose because this particular structure matches with, yes, it is structure of one of the heterocyclic compound, that is furan. This is what we call it as furan. This is furan, one of the heterocyclic compounds. The structure of furan matches with this particular structure. That's why the structure of alpha D glucose, alpha D fructose is known as alpha D fructofuranose. Your OH group is below the plane and the second carbon atom is anomeric carbon atom. In the case of glucose, first carbon atom was anomeric carbon atom. Here, the second carbon atom is anomeric carbon atom. Agboda? So that is what we call it as, yes, it is the alpha D fructofuranose. If you want to write beta D fructofuranose structure, ಏನು ಮಾಡಬೇಕು? Simply you change the configuration of the second carbon atom. Just write OH group above the plane. CH2OH group, yes, it is below the plane. This is what we call it as beta D fructofuranose. This is what we call it as beta D fructofuranose. Agboda? So this is what we call it as the Howard ring structure of alpha D fructofuranose and beta D fructofuranose, right? Agboda? These alpha and beta isomers are called as anomers because these alpha and beta isomers differ in configuration at the anomeric carbon atom. So that is what we call it as Howard ring structure of alpha D glucose and beta D glucose. As it is alpha D fructose and beta D fructose. Agboda? Example direct nimage write the Howard ring structure of alpha D fructofuranose anta keltare. Aga kelu ideas itkonbidi. Alpha D fructofuranose ಬರಿಬೇಕಾದ್ರೆ 5 member cyclic ring ಬರೀರಿ with 1 oxygen at the cyclic ring. ಈ ತರ ಬರೆದ್ಬಿಟ್ಟು look at this. Here it is CH2OH. Here it is CH2OH. Both are on the same side. CH2OH groups are cis to each other. At this is second, this is third, fourth, and fifth. The second and fifth positions only CH2OH groups are they are cis to each other. 3-4 position alli nodi. 2 hydrogen atoms are trans to each other. And this is OH, this is OH, this is H, and of course OH group below the plane. Alva? Therefore it is OH there. Yes. So this is what we call it as. Yes, it is alpha D fructo. Yes, it is furanose. ಈ ತರ ನೀವು ಡೈರೆಕ್ಟ್ ಆಗಬೇಕಾದ್ರೆ ಬರೀಬಹುದು. OH group ನ ಮೇಲೆ ಬರೆದ್ರೆ above the plane ಬರೆದ್ರೆ ಏನಾಗುತ್ತೆ ಅದು beta D fructofuranose ಆಗುತ್ತೆ. ಹೌದಾ? So this is alpha D fructofuranose and beta D fructofuranose. ಆಗ್ಬೋದಲ್ಲ? So that is what we call it as the Howard ring structures of glucose and fructose. And that completes the discussion carbohydrates. And as far as the reduced syllabus is concerned, in reduced syllabus, we don't have any discussions over disaccharides, polysaccharides, and importance of carbohydrates. And these topics are being deleted. Because of that, the next topic will be, yes, it is proteins under biomolecules. Now we'll take up proteins now. Okay, now we'll see that. Now let us see one more important discussion under biomolecules. It will be proteins. One of the class of biomolecules found in living organisms. These proteins are very, very essential for the growth and maintenance of our body. These proteins are found in every part of our body because they are playing a vital role in maintaining, yes, it is various biological functions of our body. That's why they have been given a primary importance among the biomolecules. The word protein is coined from the Latin word proteus, meaning primary. The primary importance will be given to these biomolecules because of their biological functions. Every part of our body is made up of proteins. They form fundamental basis for structure and yes, it is functions of our life. So that is what we call it as proteins. That the chief sources of proteins are, yes, it is meat, fishes, egg. Is it not? These contain what we call it as very rich protein components. At the same time, that is peanuts. They are also characterized by proteins. They are the very good sources of proteins. Apart from that, milk is a very good source of protein. Cheese is a very good source of protein. And of course, peanuts, pulses, meat, fishes, they are very good sources of proteins. And of course, these proteins are, yes, it is, they are performing various biological functions. These proteins can act like enzymes. Enzymes, they are very important biocatalysts. They are going to catalyze various biochemical reactions. These proteins can act like biological messengers. That means they act like hormones. These proteins can act like, yes, it is, transport agents. That blood contains hemoglobin. It's a protein that transports oxygen from lungs to the tissues. These proteins can act as structural materials. the shape of each organ in our body is because of, yes, it is proteins there. That's why these proteins will form a fundamental basis for structure and functions of our life. So that's why much importance will be given, yes, it is proteins as far as the existence of life is concerned. Not this moment, as far as proteins are concerned, these proteins are formed by, yes, it is combination of a large number of alpha amino acids. Or you can say, when proteins undergo hydrolysis, when proteins undergo complete hydrolysis, they produce large number of, yes, it is alpha amino acids. That means the major components of, yes, it is proteins will be, yes, it is yes, alpha amino acids. That's why these alpha amino acids are considered to be building blocks of proteins there. And as far as alpha amino acids are concerned, as many as 20 naturally occurring alpha amino acids are there. These alpha amino acids are involved in the formation of varieties of proteins with a particular, yes, it is functions. A particular protein requires particular sequence of amino acids for performing particular type of functions. So that is what we call it as alpha amino acids. As far as the structure of alpha amino acids is concerned, look at this. As the name itself indicates, these alpha amino acids are characterized by two functional groups. One is NH2 group, another is carboxyl group. This is amino group, and of course this is carboxyl group, and this is acidic in nature. Carboxyl group as well as amino group, both are found in a same molecule, that is in alpha amino acids. Therefore, the structure of, yes, it is alpha amino acids will be like this. This is the structure of, yes, it is alpha amino acids. Just observe, we call them as alpha amino acids because the amino group, NH2 group, is at the alpha carbon atom. NH2 group is attached to the alpha carbon atom. This is alpha carbon because this is a carbon directly attached to the carboxyl group. Therefore, it is alpha carbon to which amino group is attached. This is general formula of, yes, it is alpha amino acids. Just observe, R here, and different alpha amino acids have got different R groups. For example, if R is equal to H, then the alpha amino acids will be glycine. If R is equal to CS3, then alpha amino acid will be alanine. Like that, as the nature of R changes, the nature of alpha amino acid also changes. Different alpha amino acids have got different R groups. That we'll see later. Now at this moment, we'll go to the details of, yes, it is structure of alpha amino acids. As I said, in the case of alpha amino acids, amino group is attached to the alpha carbon atom. This is, yes, it is carboxyl group, and here it is NH2 group. Nitrogen of NH2 group carries lone probe electrons. Here it is a R group. As far as carboxyl group is concerned, this is acidic. In aqueous solutions, especially in neutral aqueous solutions, carboxyl groups releases H plus ions. In neutral aqueous solutions, this carboxyl group releases H plus ion because it is acidic in nature. These H plus ions will be taken up by basic NH2 group. Thereby, alpha amino acid will be converted into, yes, it is alpha amino acid will be converted into, yes, it is dipolar molecules. Look at this NH2 group. We'll take up H plus from carboxyl group and gets converted to NH3 plus. The NH2 group H plus ion carboxyl group accept ಮಾಡಿದ ತಕ್ಷಣ ಏನಾಗುತ್ತೆ NH3 plus ಆಗುತ್ತೆ. Then it is CH and of course R. After losing H plus ion, carboxyl group is converted to, yes, it is COO minus. Just observe, that is due to the donation of H plus ions from carboxyl groups to the, yes, it is NH2 group, and you are going to get, yes, it is a molecule with two electric dipoles. This is dipolar ion. No doubt it is a neutral molecule characterized by positive as well as negative charges. This is neutral dipolar molecule. Neutral dipolar molecule, and it is known as, yes, it is Zwitter ion. This is known as Zwitter ion. This is Zwitter ion form of, yes, it is alpha amino acids. This is Zwitter ion form of alpha amino acids. Example ಕೇಳ್ತಾರೆ, write the Zwitter ion structure of alpha amino acids and telling, we're supposed to write this. Okay, now this is what we call it as Zwitter ion form of alpha amino acids. As far as, yes, it is Zwitter ion form is concerned, This zwitterion form of alpha amino acids is, yes, it is amphoteric in nature. This is amphoteric in nature. That means this zwitterion form can act like an acid, can react with acid as well as base. Amphoteric substances are those substances which react with acids as well as bases. Like that, zwitterion form of alpha amino acids is amphoteric in nature because it reacts with acids as well as bases. That I can represent by using equations like this. Just observe in acid medium, right? In acid medium where the pH is less than 7. In acid medium, just observe. This is yes, it is NH3 plus CH and of course C double bond O minus. This is zwitterion form of alpha amino acid. In presence of acid, that is H plus ion, when pH is less than 7, it will be converted into, yes, it is positively charged ion. It will be converted into, yes, it is positively charged ion, or you can say that cation. CO minus absorbs H plus and gets converted to COH. And of course, in acid medium, amino acids will be in the form of cations. In acid medium, amino acids will be in the form of cations. Therefore, these amino acid molecules in acid medium, they are migrating towards cathode under the influence of electric field. And of course, at the same time, in basic medium, right? Look at the zwitterion there, NH3 plus. How it behaves with basic medium, like this. This is OH minus in basic medium where pH is greater than 7. When pH is greater than 7, OH minus ions from basic medium interact with NH3 plus. Thereby, NH3 plus loses H plus and gets converted to, yes, it is NH2 there, CHR, and of course CO minus plus water. Look at this. In basic medium, alpha amino acids will be in the form of negatively charged particles. In basic medium, alpha amino acids will be in the form of negatively charged species. Therefore, in basic medium, alpha amino acid molecules will be moving towards positively charged electrode, that is anode, under the influence of electric field. And just observe. In acid medium, when pH is less than 7, in acid medium, when pH is less than 7, alpha amino acid molecules are moving towards cathode. When pH is greater than 7, alpha amino acid molecules are moving towards anode. And therefore, at one particular intermediate pH value, alpha amino acid molecules do not show any migration towards either electrodes under the influence of electric field, and that particular pH is called isoelectric point. That is, isoelectric point is a pH of alpha amino acid. Under that pH, alpha amino acid molecules will not be showing any migration towards either of the electrodes under the influence of electric field. So that pH is called isoelectric point. This is what we call it as isoelectric point. And of course, as far as the alpha amino acid glycine is concerned, its isoelectric point is 6.1. As far as alanine is concerned, its isoelectric point is 6.0. As far as aspartic acid is concerned, its isoelectric point is 3.0. As far as lysine is concerned, its isoelectric point is 9.7. Like that, isoelectric point is a pH of a solution, pH of a medium, under which, alpha amino acid molecules will not be migrated towards any of the electrodes under the influence of electric field. Such type of pH value is what we call it as the isoelectric point. Yes, it is. So, in the examination, you are supposed to write zwitterion structures of some, yes, it is alpha amino acids. Now at this moment, I am going to take up, yes, it is next discussion, that is structures of some naturally occurring alpha amino acids. And as many as 20 naturally occurring alpha amino acids are there, but we are going to discuss only 10, the structures of 10 naturally occurring alpha amino acid molecules. We'll see that. Structure of, yes, it is a structure of, yes, it is alpha amino acids, right? This is. Now let us see structures of some naturally occurring alpha amino acids. The The general formula of, yes, it is all amino acids will be NH2 and it is R, and of course, yes, it is COOH. This is general representation of alpha amino acid. This is alpha amino acid. Yes. As the nature of R group changes, the alpha amino acid changes. Different alpha amino acids have got different R groups. Let's observe. If R is equal to H, it will be glycine. It will be glycine. Let's observe the structure becomes NH2, CH2, COOH. Just observe here. This is glycine. This glycine does not contain any asymmetric carbon atoms. No asymmetric carbon atoms are found in glycine. Therefore, it is optically inactive. This is optically inactive. Yes. Except glycine, all alpha amino acids are optically active. But glycine is optically inactive because it does not contain asymmetric carbon atom. You know, asymmetric carbon atom is a carbon atom attached to 4 different groups. ಇಲ್ಲಿ R ಕೂಡ ಹೆಚ್ಚಾಗಿರೋದ್ರಿಂದ CH2 ಆಗಿಬಿಡುತ್ತೆ. Therefore, asymmetric carbon atom is absent. Therefore, it is optically inactive. And of course, it is named as glycine because of its sweet taste. Because of its sweet taste, you know, the compound, that alpha amino acid will be named as glycine here. Just observe if R is equal to CH3 adre, it will be alanine. It will be alanine. Look at this. This is NH2. R ಬದಲಾಗಿ ಏನು ಹಾಕಬೇಕು? Yes, it is CH3 ಹಾಕಬೇಕು, and it will be COOH. And of course, this is optically active with one asymmetric carbon atom. ಹೌದಾ? Look at this. If R is equal to CH2 C6H5. If R is equal to CH2 C6H5, then it will be phenylalanine. That will be phenylalanine, and of course the structure will be, look at this, NH2CH. ಇಲ್ಲಿ R ಬದಲಾಗಿ ಏನು ಹಾಕಬೇಕು? CH2 C6H5. This is CH2 C6H5, and of course COOH. This is what we call it as phenylalanine. ಆಗ್ಬೋದಾ? ಹಾಗೇನೆ if R is equal to CH2OH, again, look at this. If R is equal to CH2OH, right? If R is equal to CH2OH, then you are going to get one alpha amino acid, that is serine. Look at this structure. You can write NH2, and of course CH. R ಬದಲಾಗಿ ಏನು ಹಾಕಬೇಕು? CH2OH, and of course COOH. This. If R is equal to CH2SH ಅಂತ ಆದರೆ, OH ಬದಲಾಗಿ SH, then it will be cysteine. And it will be cysteine. Just write NH2, and of course CH. ಹೌದಾ? NH2CH. R ಬದಲಾಗಿ ಏನು ಹಾಕಬೇಕು? Yes, it is CH2SH. This is the amino acid containing, yes, it is the sulfur there. This is what we call it as cysteine there. If R is equal to CH2, yes, if R is equal to CH2 and COOH, then it will be aspartic acid. That will be aspartic acid. Yes, its structure is, yes, it is CH2CH, and it will be CH2COOH, and it will be COOH. Just observe, in the case of aspartic acid, the molecule of aspartic acid contains 2 carboxyl groups and 1 amino group. Howda? Number of carboxyl groups will be more than number of amino groups. Therefore, this aspartic acid is an example for acidic alpha amino acid. Just observe here, number of amino groups will be equal to number of carboxyl groups. This cysteine is what we call it as neutral alpha amino acid. Number of amino groups will be equal to number of carboxyl groups. Serine is an example for neutral alpha amino acid, but here number of carboxyl groups will be more compared to the number of amino groups. 2 carboxyl groups ಇದೆ, 1 amino group ಇದೆ. Therefore, it is an example for acidic alpha amino acid. Like that, you know, if R is equal to, look here, if R is equal to CH2, CS2, yes, it is COOH, and the amino acid is glutamic acid. Amino acid is glutamic acid. Look at the structure here. NS2CH. ಇಲ್ಲಿ R ಬದಲಾಗಿ ಹಾಕಿ CH2, CH2, COOH, and of course this is COOH. This is also an example for acidic amino acid. Look here. If R is equal to CH2, 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 NH2 ಅಂತ ಇಟ್ಕೊಳ್ಳಿ. ಆಗ it will be, yes, it is lysine. Look at the lysine here. This is NH2 and of course CH. This is CH2, 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 NH2, and of course this is COOH. Look at this. Number of amino groups will be more than number of carboxyl groups. So this is an example for basic alpha amino acid. This is an example for basic amino acid. Like that, you know, if R is equal to, yes, it is one more alpha amino acid, that all right? Yes. If R is equal to, look at this, CH2, and of course this is phenolic group, right? And of course this is tyrosine. It is named as tyrosine because it is obtained from cheese. Okay, na? And of course this is structure is NS2CH. Look at this CH, and of course benzene ring, and of course OH. Howda? R ಜಾಗದಲ್ಲಿ ಹಾಕಬೇಕು CH2, and of course C6H4, and of course OH. And this is, yes, it is the tyrosine, and of course it's also neutral. Yes, it is carboxyl neutral alpha amino acid. Yes. Like that, you know, we have one heterocyclic amino acid. Actually it is amino acid because here we have amino group. This is yes, it is look at this carboxyl group. Yes, it is. Okay, na? Here amino group, and of course this is secondary amino group. The cyclic ring, it is amino group. Therefore it is amino acid. You can call it as, it is amino acid, or you can say heterocyclic alpha amino acid. Its name is proline. Its name is proline. Yes. These are the structures of some alpha amino acids. The structures of some alpha amino acids. In one of the question papers, you know, the question was asked like this: write the zwitterion structure of alanine ಅಂತ ಕೇಳಿದ್ರು. First ನಿಮಗೆ ಗೊತ್ತಿದೆ, you know the general formula of zwitterion, NS3+, and of course R, and of course COO minus. This is zwitterion form of alpha amino acids. Alanine ಅಂತ ಕೇಳಿದಾಗ R ಜಾಗದಲ್ಲಿ CH3 ಹಾಕಿ ಅಷ್ಟೇನೆ. This is zwitterion structure of, yes, it is alanine. Write the zwitterion structure of glycine ಅಂತ ಕೇಳಿದ್ರೆ ಇಲ್ಲಿ H ಹಾಕಿ ಅಷ್ಟೇನೆ. Write the zwitterion structure of phenylalanine ಅಂತ ಕೇಳಿದ್ರೆ ಇಷ್ಟೇ ಬರೀರಿ. This is phenylalanine, zwitterion structure of phenylalanine. ಈ ತರ ನೀವು ಬರೀಬೇಕು. ಓಕೆನಾ? So this is what we call it as the structures of some alpha amino acids. Apart from that, you know, as far as amino acids are concerned, these alpha amino acids are optically active, except glycine. All alpha amino acids are optically active with one asymmetric carbon atom. Look here, this is in the general structure of, yes, it is alpha amino acid. This is R, this is H, and of course this is NH2. This is general structure of, yes, it is alpha amino acid. And of course, as far as the configuration of alpha amino acids are concerned, this is what we call it as L configuration, where NH2 group is on the right side. If NH2 group at the asymmetric carbon atom is on the right side, if NH2 group at the asymmetric carbon atom is on the right side, it will be, yes, it is D configuration, we call it as. This will be D configuration ಅಂತ ಕರೀತಾರೆ. NH2 group ಎಡಭಾಗದಲ್ಲಿದ್ರೆ L configuration ಅಂತ ಕರೀತೀವಿ. And of course all naturally occurring ಅಥವಾ most of the naturally occurring alpha amino acids have L configuration. They contain NH2 group on the left side of the asymmetric carbon atom. Yes, this is the Fischer structure of, yes, it is alpha amino acid. Where NH2 group is on the left side, it will be L configuration. If NH2 group is on the right side, it will be T configuration. So this is what we call it as something about alpha amino acids. Yes, and of course apart from that, you know, as far as amino acids are concerned, amino acids can be classified into essential amino acids and non-essential amino acids. Essential amino acids are those amino acids which cannot be synthesized in our body, which should be obtained through our diet, which can be obtained through our diet, and they are called as essential amino acids. Example for the essential amino acids will be lysine and leucine. They are the examples for essential alpha amino acids. At the same time, some alpha amino acids are synthesized in our body and they are non-essential amino acids because they are already synthesized in our body. Whatever the amino acids that are required for our body, which will be synthesized in our body itself, and they are not essential. Because of that, non-essential amino acids are the amino acids which can be synthesized in our body. An example for the non-essential amino acids will be glycine, alanine, phenylalanine, proline. They are all examples for non-essential amino acids. Essential amino acids are the amino acids which cannot be synthesized in our body, which should be supplied to our body through our diet. These amino acids are to be supplied to our body through our diet, and they are called as essential amino acids. So this is what we call it as the classification of alpha amino acids. We classified alpha amino acids into acidic alpha amino acids, basic alpha amino acids, and neutral alpha amino acids. Neutral alpha amino acids andre the alpha amino acids which contain equal number of amino groups and carboxyl groups. If alpha amino acid contains equal number of carboxyl groups and amino groups, and they are called as neutral amino acids. If number of carboxyl groups are more than the number of amino groups, they are called as acidic amino acids. If number of amino groups are more than number of carboxyl groups in a molecule of amino acid, and they are called as basic amino acids. So acidic amino acids ge aspartic acid and glutamic acid kodbodu. Basic amino acids ge lysine kodbodu. Neutral amino acids ge glycine, alanine, phenylalanine, cysteine, serine, avallo kuda neutral alpha amino acids. So that's all about the alpha amino acids. Remaining things we'll see in the next video. Thank you, right?